Okay, good morning. Welcome to
Math number
78. 78. Okay, so today I thought it'd be real fun to do a different kind of family math. We may do some of these this summer where we, instead of doing math that you guys know, I might introduce you to some really cool math because there's a lot of neat things going on in math right now.
Okay.
So today I thought we'd talk about continued fractions. And continued fractions are a little bit different than regular fractions. Like I have some regular fractions over here, 3/2, 7/5.
Squared.
17/12, things like that.
Yeah.
But over here I have a different kind of fraction. 1 plus 1 over 2 plus 1 over 2 plus 1 over 2 plus 1 over 2 plus 1 over 2. It goes on forever, infinitely far down. It never stops. Would you like to finish writing it out for me?
Okay.
Yeah.
How long do you think it would take to write out?
Infinity.
Yeah, infinity. It'd be a long time. But this is a neat fraction. What I can do is I can stop right at the beginning and I just get 1. If I stop right here, I get 1 plus a half. And what is 1 plus a half?
3/2.
3/2. And why is that?
Because 1 is 2/2.
1 is 2/2, so I get 3/2. If I stop here, it turns out I get 7/5. And can you tell me what you have to do to show that 1 plus 1/2, 1 plus 1 over 2 plus 1 over 2 is a half? Or is 7/5?
Well,
Sorry.
you have to start at the bottom and work your way up.
You have to start at the bottom and work your way up. Okay, very good. And the next one, when I get down to here, and I did the approximation here, what would that be? Can you tell me?
7/12.
17/12?
Wow.
Yeah, good job. How'd you know that?
And then
I followed there.
Oh, you followed over here. Okay. So we get, as I go down this continued fraction, I get these fractions. 1 3/2, 7/5, 17/12, 41 29s, 99 70ths, and I keep going down forever. And these are interesting numbers, but it's hard to see what they mean. But what if I square them? 1 9/4, 49 25ths, 289 over 144, 1681 over 841, 9801 over 4900. Now these numbers have some interesting relationships. Do you see anything that's related with these numbers? It's a little tricky to see, but you might be able to see it.
Well, I
What's
know
special about the top and bottom of
they're
these
both
numbers?
squares.
They are both squares. Do you see anything else that's special? What is 9/4 about equal to?
It's about 10. It's about 8/4, which is 2.
Okay. What's 49 25ths about equal to?
50 25ths, which is 2. So
What's 289 over 144 about equal to?
about equal to 2.
Do you know what 841 times 2 is? Do you know what 841 times 2 is?
Pretty close to 2.
No, 841. What is 841 times 2?
Well,
What's 800 times 2?
1682.
1682. If I multiply this by 2, I get 1682, which is really close to that.
Yeah.
So this fraction is also about equal to 2. And 4900, do you know what 4900 times 2 is? 4900 times 2?
It's 8,000 plus. It's 9800.
9800. How about that? So when I square all of these fractions, I get something very, very close to 2. And what number squared equals 2? Can you tell me?
It's the square root of 2.
Okay. So it turns out that this continued fraction, and you can prove this mathematically, is equal to the square root of 2.
Wow.
Wow. Now, have you ever heard about the square root of 2 before?
Yeah.
Yeah. It's actually an irrational number, and usually people think that irrational numbers don't have any patterns. But look, do you see a pattern here? 1, 2, 2, 2, 2, 2, 2. Do you see the pattern?
Yeah, it's
1
one half.
1 1 1 1 1
half.
1 1 1 1 2 2 2 2 2 2.
Except for the 1 at the beginning, it's all 2s and all 1s. Well, that's a pattern. So this irrational number does seem to have a pattern if we look at it this way. Now, can you erase just the 2s for me? Please, do you have an eraser? Do you have an eraser? Can you erase just those 2s for me while I erase over here? So when I go 1, 2, 2, 2, 2, that gets me the square root of 2. Instead, if I go 2, 4, 4, 4, 4, 4, if I double all the numbers,
You still make.
2, 4, 4, 4, 4, I get the square root of 5.
Whoa.
It's not strange, I doubled everything, but I didn't double this. It went from the square root of 2 to square root of 5. Can you erase it down from the top? If I triple the numbers and go 3, 6, 6, 6, 6, 6, etc. You know what I mean, right? Down the diagonal here. I get the square root of 10. If I go 4, 8, 8, 8, 8, I get the square root of 17. If I go 5, 10, 10, 10, 10, I get the square root of 26. Now, this is a tricky pattern. I'm going to do one more and then ask you what the pattern is?
Okay.
Or do you want to try to guess it from here?
Well, they're all very close to squares.
2, 5, 10, 17, 26. What do you think the next number is in this pattern?
They're all one more than a square.
So what would the next number be?
1 squared, 2 squared, 3 squared, 4 squared, 5 squared. So I think it's 37.
37, that's exactly right. 6, 12, 12, 12, 12 gives me the square root of 37. So some of these numbers, some numbers, have square roots that have really interesting patterns in continued fractions. And I'm going to write a new one on the board just to show you that continued fractions just aren't simple square roots. I'm going to write a new continued fraction that's going to help you figure out pi. Cool. So hold on, let me just turn the camera off. This is going to take a little while to write.
Okay.
Okay, so here's an interesting continued fraction that helps you think about pi. So we have the fraction 4 divided by pi equals 1 plus 1 squared over 2 plus 3 squared over 2 plus 5 squared over 2 plus 7 squared over 2 plus, what do you think the next term over here would be?
Maybe 9 squared.
squared.
9 squared, and what do you think would be down here?
11 squared.
2 plus
9 squared.
11.
9 squared's here.
11.
11 squared. We keep going on forever. Now remember, with the square root of 2, we had 1, 2, 2, 2, 2, 2 down like this. And then we just had 1s over here. To get 4 over pi, we have 1 squared, 3 squared, 5 squared, 7 squared, 9 squared, 11 squared. It's pretty neat, right?
Interesting.
Yeah.
So you hear about pi and people say, oh, there's no pattern for pi. But here's an expression for pi that does have a pattern. Is that interesting?
Yeah.
So continued fractions used to be studied really thoroughly in math. And you know what the sad thing is?
What?
No one really studies them too much anymore. They used to even be, I think, taught in high school, but they're not taught in high school anymore because people just think they're not important. And they're not really studied in college that much anymore either because people think they're too simple, I guess. I'm not sure. It's too bad though. It's a really beautiful subject. And there was somebody, a famous mathematician named Ramanujan from India was great at continued fractions. He was like super continued fraction guy. He wore a cape and it had continued fractions on it. That was his secret power. Pretty cool, right? Is that fun?
Yeah.
Is this a neat topic? Would you guys like to learn more about continued fractions?
Maybe.
Maybe?
Yeah.
Okay. You would?
Maybe.
What do you think you need to learn first before we study continued fractions?
Fractions.
Regular fractions, probably.
Yeah.
It's okay. Sometimes it's fun to learn about new stuff. All right, high five. Great job today, guys. Great job.